When we work with the law of conservation of energy, we're always making assumptions. This lesson is about identifying those and identifying how they might influence our results. So the learning objective is I can identify and describe the limitations of the computational model based on the assumptions that were made. When we do a conservation of energy kind of problem, we are always going to be assuming some things. Some examples: air resistance. These assumptions can help us make the math easier. If we were to write the true conservation of energy equation for an object falling, we would have to include every single air particle that the object hits on the way down and how much energy it gives it from the collision between itself and the object falling, the air particle and the object falling. Billions upon billions or trillions upon trillions of air particles as it passes through the air. This would become impossible to calculate. So we make some assumptions, and they make the math a lot easier, and they make us be able to run simulations faster, but they don't always match reality. Some assumptions are more valid than others. Some assumptions come with less negative impact to our calculations than others. And it's important to identify whether the assumptions you're making are going to cause significant error in the results you get, or negligible, which means very small amount of error in the results. Well, let's go over some common assumptions when working with these conservation of energy equations and problems. One of the first ones is neglecting air resistance. This is very common because the math for air resistance is a bit trickier, and to actually model how fast an object is going in the air requires higher level calculus because the force of air resistance actually increases as the object picks up speed. So how much it's pushing back is a function of how fast it's going, but it also determines how fast it's going to go. It's sort of circular. There's a math that's used to figure that out, but it is more advanced than we're covering in this course. So we often ignore air resistance. However, we ignore it, but we identify that we have ignored it. When we drop an object and we notice that it took a longer time for it to land, or it's going slower when it lands than our calculations say it should go, we should expect that. We should expect that objects, when they hit the ground or hit our final destination, wherever that is, that they are going slower or they took more time because of the real force of air resistance. Another assumption we make is constant mass. Now, this assumption is often pretty valid. In everyday situations, an object isn't losing its mass. However, one that it really affects is rockets. You cannot apply the conservation of momentum or conservation of energy in the same way for a rocket as you would for an object, a ball thrown in the air or something. A rocket does not have the same mass the entire time. An easier example, actually, is if you were to take a balloon. So in a balloon, where it has the place where you put your mouth and blow it up, if you were to blow up a balloon and then let it go, air is going to be expelled out of the balloon, pushing the balloon forward. But air does have mass. So as the rocket, in this case, pushes air out, it undergoes a combustion reaction that causes gas to violently shoot out of it. All of this gas does have mass. And we know that's definitely the case because as it's burning fuel, the tanks will empty. And an empty tank definitely weighs less, definitely has less mass than a full tank. So rockets are a real good example of where we have a situation where the mass of an object is actually changing while it's going. This, just like the air resistance problem, does lead to some math where some more variables are changing continuously as time goes on and makes the math a bit trickier to solve. And although it makes the math easier to solve, it would not be very valid for a rocket for you to use the assumption that mass is constant. When we talk about assumptions that are more valid than others, this is a very not valid assumption for a rocket. It is a valid assumption for a ball thrown up in the air, or even that balloon example that I mentioned earlier. That one would be more correct or more valid to use that assumption because the air is so light compared to the balloon itself. Another common assumption we make in physics is treating an object as a point particle. What this means is we take an object and we reduce it down to just a point, and we just pretend it's an infinitely small point, that it doesn't have volume. Some of the physics gets harder when you have an object that actually has volume, because then you have to take into account rotation. An object rotating acts a bit differently than an object not rotating. Another thing, we haven't gotten to the equation of force acting at a distance, but it does matter how far away an object is. So the force that the Earth is pulling on the moon, on the side of the moon that's closer to Earth, is greater than the force of attraction that the Earth is pulling on the part of the moon that is the furthest away. It's often not a very big difference, so it's often negligible. The distance from the Earth to the moon is not well represented by this diagram. The distance from the Earth to the moon is much, much, much greater than the diameter of the moon itself. So the difference in force between one side of the moon and the other side of the moon is going to be very small. It does matter for some solar systems, some objects going in orbits. It can make a significant difference. We often call those tidal forces. But for the case of most of the physics that we do, at least in this class, we can treat the moon as a point particle and pretend that all of the mass is in one point and it's all being pulled the same towards Earth. So that's the point particle assumption. Another one we do a lot is ignore friction. The real cause for friction comes from these surfaces that are not perfectly even, and the little cracks and crevices will align such that they actually will repel each other. This is going to slow down an object. This is going to take energy out of the system. Whichever direction this object is trying to go, whether actually moving because of a velocity or it is just has a net force in one direction, whichever way object is trying to go, the force of friction is going to oppose that. This reduces the energy in a system at a later point in time, or at least we know that it gets turned into thermal energy. Thermal energy, though, is not very useful in most situations, so we often talk about it being reducing the energy. Another common assumption we make is using ideal conditions. This is often the case with springs. The equation for the force of a spring is actually negative kx, where k is just some constant, times x, which x is how far you stretch the spring. But this is not always true. In fact, this is an assumption. This is something called Hooke's law, and Hooke's law is only true in what we would call ideal springs or perfect springs, but not everything that has an elastic force is a perfect spring. In fact, there is no such thing as a perfect spring. Then we also talk about perfectly elastic collisions. No collision is perfectly elastic, but we often will pretend that it or assume that it is. Collisions that are close to perfectly elastic, it's a valid assumption. However, if you were talking about an egg that splats on the ground, it would not be at all a valid assumption to say that it was a perfectly elastic collision and use the physics based on that. Real-world systems are not ideal, but the assumptions we make allow us to describe situations and phenomenon using mathematics. But how valid that application of mathematics is all depends on the assumptions you made and how valid they were. But then that brings up a good question. Why do we even use these models if we know that they're going to be incorrect due to assumptions? Why not just use the more correct one? Well, let's say we had a model, gotten a force of something, but didn't take into account air resistance. Doesn't matter what the situation is. You just solved a problem and you assumed no air resistance. And you got the force that you were solving for, whatever that might be, of 205.6 newtons. And then let's say you had a more complicated model that actually took into account air resistance. And now you got a force value of 205.601. Adding air resistance, which required much more complicated math, much harder process, or more calculation time for a simulation, added percentage-wise a very, very small difference. If that costs either your own time to calculate or computational time on a computer, if you're probably going to round to the nearest tenth anyways, that air resistance model is not needed. It's way too precise for the results that you were looking for. So if the difference between a more accurate model and a less accurate model is small enough that it will have no practical bearing on whether you decide to do one thing or another, then just go with the simpler model. In science and engineering, we would say that the effect of an assumption is negligible, and negligible is a scientific way of saying that so small it does not matter. Another situation, similar to what I previously mentioned, is technically the top of your body feels less of a pull than your feet. But we never think about this effect, though. I never feel like my head is pulled less towards Earth than my feet. But that's because the difference is incredibly small. However, there is a circumstance where this effect could make a huge difference. If you were approaching a black hole and going inside a black hole, the force of gravity gets so strong and so dependent on how far away you are that the force your feet would feel will be so much greater than the force that your head feels. And this effect is theorized to be so strong that it would essentially split your body or just like stretch your body so much that you will become spaghetti. So here, in a black hole situation, it would matter. On Earth, obviously it doesn't. The situation will determine how valid your assumptions are. Just because an assumption is negligible in one circumstance does not mean it always will be negligible. You must ask yourself, what assumptions am I making, and will they significantly affect my results? And a good scientist would also think of how might they affect it?